code in it? Like everything?
It's pretty flexible, actually. It's like even it's yeah, definitely easier to manage. No, yeah.
Okay, so what I want to do today is finish the CBR translation that we didn't go through last time at a leisurely pace. Start with a little refresher of what we did last time with clarifications of what I didn't quite know how it works. I hope like you, like me, you reread the entire guide into macros and half of the reference manual. And I hope you can quote from it. Anyway, so remember we started by drawing a distinction in Racket. The syntax is sort of like the quoted pieces of code, except it's a distinct data type for two reasons that we'll cover soon. And the operator that distinguishes the scheme quasi-quote and the unquote, which allows you to evaluate an expression and put the result into syntax, is called syntax in full form. Okay, and there is of course a variant for unquoting in Racket syntax. Okay, so there is nothing special except there is a parallel set of operators that produce not an S expression but what they call a syntax. But you can think of it as abstract syntax trees over which all macro expansion happens. You can convert between the two, right? You can remember this is a single function with a name that suggests it's a conversion. So nothing special, I think, was to be mentioned here. Okay. What is interesting is why there are separate syntax objects. So one reason that we mentioned was that the syntax object comes with information that refers back to the source code, line number, column, and so if there is a syntax error or runtime exception, if you have access to the syntax objects, you can highlight the error directly in the Racket editor. Okay. There is another reason that is a little bit more fundamental, but let's first actually narrow down what the syntax are. So the syntax are trees that contain just symbols, which are names of functions and operators, sort of like strings, but used exclusively to name objects. Then constants, like 1, 2, 3, okay, and then lists, in fact nested lists that construct the tree. So that's all there is to it. And of course, in addition to it, there is the source line, source code information. But there is sort of a more fundamental reason that actually facilitates the rewrites, and that's the lexical binding information. So when there is a symbol that refers to an identifier in the program, you actually know what it binds to. And you can ask questions such as taking two pieces of syntax, okay, and asking whether they do bind into the same variable. So you ask if these are free identifiers, okay, are they equal in the sense that they refer to the same thing? So in this case, they are. You can also see on this example that two instances of a car do not refer to the same identifier. Why? Because this one is created at one level, and this one is created inside this let expression, right? So this one here actually binds to this, and therefore, in the free identifier sense, they are not equal. Right, so this example, although simple on the surface, really shows you the power of what Racket does. Here is a piece of Racket code which introduces a new local scope, introduces a new variable which happens to have the same name as this one, okay? And it takes this part of the code, turns it into a syntax, and returns it, right? This let expression evaluates to what? This let expression evaluates to this, okay? And so its value is this piece of syntax. It carries with itself what it is bound to, and this binding allows you to distinguish this car from that car, that symbol from that symbol. And this lexical binding is also used for renaming. Right? Remember the hygienic macros? We'll go through it briefly. To avoid conflicts, new names are created. Use this lexical binding to avoid conflicts. Okay. So, what are macros? Here is a definition of swap. Right? Swap has a name, which is what triggers the macro, 2 arguments. Okay? And what it does, creates a new temporary variable, assigns to it the value of x, and then it assigns to x and y. But what are x and y? Since macro is essentially inlined, it assigns into the arguments of swap. Okay. Here is an example of what potentially could happen, right, if renaming of variables was not done correctly. What we have here is a piece of code that invokes swap, defines temp variable, which happens to have the same name as the one here. So this piece of code is effectively inlined in here, and now we would have one temp and another temp in the same scope. And the way the renamer deals with it, that gives them separate names. It distinguishes one from the other by renaming them. Nothing special here, but we'll use it to accomplish a trick later in the CBR implementation. Okay, so what is really going on? There is almost at the lowest level is this construct syntax case. What does it do? It accepts a syntax tree, and then it checks whether this pattern matches at the root of the syntax tree. And if it does, it replaces it with this result. Okay. What about the deep subtrees of the tree? Well, using template variables, you can carry parts of the source tree to the target tree. How does it happen? Well, here is a syntax case. Here is the source tree. Here is the pattern. The pattern matches because all 3 are free variables, and so op matches with plus. And 1 is bound to 1 and 2 to 2. Okay. And now if you look at what is output, it's a piece of tree where the subtrees from here are plugged in here for n1 and n2. These don't have to be constant, they have to be could be arbitrary subtrees, and often they are. Okay. So far so good. Okay. So this one, the syntax case, looks at this tree here, this one, and only checks what's going on at the root. So it applies these patterns here, this one here, only at the root. So we need something that will walk through the entire tree essentially and find instances and rewrite them. And this is define syntax construct. What does it do? It says essentially go through the tree, find instances of swap in it. If we find them, then apply the syntax case, which we just saw on that subtree. So you can think approximately of the defined syntax as something that walks the tree and does the rewriting on the tree. Of course, it all happens dynamically during parsing as the tree is constructed, but in most of the cases you can think of it that way. Right? Really, how it happens when a match is found, so there is a node called swap. Right? So we find somewhere in the program an S expression that has swap right next to the left parentheses. On this subtree here, we invoke this lambda, and we pass this subtree as an argument to stx. And then the usual thing happens inside. We match a pattern, bind x and y to the subtrees, and generate a piece of syntax that contains the new code with x and y bound to whatever they were bound here. Presumably, in this case, these arguments that I didn't fit into the parentheses.
So what happens if you like locally redefine swap to be a function or something? Does the replacement take precedence, or the like?
If you locally within this scope,
yeah.
It really depends what is the scope of these two. If the macro is in scope of the definition, I assume it will rewrite the uses of that function, right? because that rewrite happens before you do evaluation. I'm guessing if I can picture the scenario you have in mind. Am I right, Amina?
Probably. I mean, if you have a name clash, it's gonna complain. But otherwise, whichever one you define last takes precedence. Let's go with lexical scope. Right. Only one of them will be in scope at a time, not both.
But no, what if you like define the macro, and then in scope of the macro you say let swap be plus, for example.
Definition where you use the name swap. You use the name swap in the definition.
No, but define syntax only looks for swap at the root, not.
Okay, so then let swap be
I think the case you have in mind is
So let swap be plus and then say swap 2, 3. What would happen then?
so you want to define a macro, right? Define syntax rule, and this will be swap. And now inside here you will say
No, outside.
outside here
Below the syntax.
below the syntax.
After the macro is defined.
Okay, so the macro ends here. And so now we introduce a function. And whatever comes here. Okay. So now we have two definitions, one and the other in the same scope. So assume here we should get a name clash, right? Because it is just a redefinition of a symbol within the same lexical scope.
I think his point
So
was.
what if instead of define you used let? So like let swap equals some function. Because let should just
Create
be
a new
scope, right?
Let creates a new scope, and within that scope, so if we do let here,
Swap be
and
plus.
now we do the swap and something, right? Now this is a new scope here that is different from the scope in which this swap is visible. So this one overrides that one and takes precedence within this scope. That's what I'm guessing will happen, but I would rather verify before check. So now we have a situation where we introduce a lexical scope. There is a new swap symbol here. There is an outside one. This one shadows that one, right? So normally it would cover it. There is the only, I guess, doubt you have is that the rewriting happens before expansion, but they really are interleaved. So I think this one will shadow that one, even though they are interleaved.
But I can check now. I'm pretty sure you're right.
That's why we have interpreters, so that you can check it.
Either it finds the paren swap times paren and it says this is not the right amount of arguments for this macro.
In here,
Yes.
Yeah, but when you call swap,
That's assuming that the.
well, this macro here looks for instances of swap that are next to the left parentheses.
well, it
But it
also
is
has to
plus.
be a 3-element
This is
list.
where-
It has to be that.
So it just basically overrides.
It overrides it.
Yeah. So inside of the left, whatever you define swap to be, it's
And if this is defined, it complains about double definition of.
If it's defined, it complains about the definition.
Okay.
Yeah.
Good. So it has sort of the usual meaning, which should be reassuring. There are no surprises about phasing in this context. The scoping of these symbols, whether they are bound to a. So this is a symbol that is bound to a rewriter essentially, and this is a symbol that is bound to some value. If this is defined, it would be bound, well, again, the same thing, just in a different scope. So rules remain the same, which is great news, I suppose. Okay, so if we go down into the lower level case, the syntax case, right, which receives a tree, and now it has pattern and the rest, right, and the result of the rest should be a piece of syntax. The rest is actually a piece of code that evaluates, but evaluates to a piece of syntax. The fact that this can be arbitrary code, remember, allows us to do checks that the macro is applied on the right arguments. Not the right number of arguments, but the arguments of the right type. So here we can check that both x and y are actually identifiers, as opposed to 1 plus 2 expressions. Okay. Now, what we talked about last time, why we cannot say instead of this just x. Okay. And Ali tried it, and the error message was that you cannot use pattern variables, right? What are pattern variables? These are variables introduced here, and they are bound to whatever swab is expanded to, right? To the argument of swab when swab is being expanded. They are not normal variables, they are pattern variables. They are bound and used at macro expansion time. So you can think of it as there is a macro expansion interpreter which has its own variables, its own environment that binds its variables to something. And then there is the evaluation interpreter with its own variables and its own binding. So these are pattern variables, which means they exist and their binding is considered at macro expansion time. So they should really have different fonts so that you can distinguish them, but pretend they do. So these are template variables sort of visible to the macro expander. And so it looks like we could just use X inside this regular bracket scheme code without that, right? Because that variable presumably holds a piece of syntax or points to a piece of syntax, and you know, the bracket code would just evaluate, and the value that would be there would be a piece of syntax. So it looks like fundamentally it could work, but they don't allow it. They say you can only use pattern variables like X and Y inside templates. And what is a template? It's anything that is sort of inside here, inside the scope of the pound sign quote. This is the only place where these variables can be used. Whether that's a fundamental reason or just to simplify implementation so that the pattern matcher only needs to look inside templates, I don't know. I feel like it might be the second, because in principle, it looks like I could put such a variable just anywhere without nesting it inside this template, and it would just evaluate to the syntax. So I don't know whether it's fundamental or some pragmatic restriction. What do you need to know? That these template variables need to reside in here. Okay. You can think of this template as a piece of code that evaluates to syntax, and you can plug other syntax into it. That should be all, I think. Okay. We looked at how to define factorial with macros, and I'll just show you the 3 versions. The first 2 don't work, but I have all 3 of them here because they show the rules at different level of abstraction. So here is the defined syntax rule, which is the simplest, and here is the pattern, and here is the code, which is already a template. You do not need to nest it into pound sign quote. This already is implicitly nested. Here is something that is sort of intermediate level, syntax rules. It allows you to do cases, but this is still implicitly converted to a template. Okay? You cannot mix on this right-hand side code and templates. And this is the lowest level where you have syntax case, where no implicit conversion happens. You need to decide yourself what is a template and what is not. So this returns a template, a syntax, and here you can mix and match, right? The whole thing here is a template, but here we are escaping to evaluation. Here we again get a piece of template and use that to convert it from syntax, to a value on which we can do then subtraction of 1. Okay? All right. We looked at application expansion. This is not so important. Okay. One thing we didn't look at is ellipsis. This is pretty cool. It makes the rewrite rule extremely compact. It looks like they really got it right, at least looking at the examples in the tutorial. So this is the highest level rule, right, which is name of a macro and arguments. And this is the template, so it expands into this. So this just generates a list, okay, that list. And the dots are essentially a clean enclosure. It's almost as if you said 0 or more arguments will match. So it's easy to understand the matching, that it is happy with 0 or more arguments. What is interesting, how you can use it when expanding. You can now say, put all of them right here. So here, when you match foo, the arguments will be just placed here, plus will be added here as well as 1. More interesting is when you do it this way. So what do you think this does? Yes.
It maps over the list of argument values, and for each one it creates that list plus 1 arg.
Exactly. So it walks over them. So this is sort of a map, but each of them is wrapped now into this piece of code. Okay? Syntax in this case. So you can now do something for all of them. And this is useful for introducing definitions, because what you inserted here could be an entire big definition. In fact, an entire new macro could be introduced that way. Okay? So let's see at what this does when you run it. When you match the first macro, you get what you expect, right? Here is a list within a list. Why? Because we have one list here and another one is created right there. And the other one takes 1, 2, 3 and wraps them in this. Okay? I think that's all we need to know, that this is sort of a loop, but it doesn't need to loop over the original argument. It can wrap it in, whatever. It also works over multiple ones, and we'll see examples of that. Okay? Now, what will happen if you have the ellipsis here and you drop it in here?
Error.
It will complain that you sort of have a mismatch. So it does a reasonable checking. So here, let's go to the CBR, which is a pretty nice test case of these facilities. Okay, so let me remind you what we want. We would like to define a function here named f with 2 arguments a and b and some body in here. But we want it to be called by reference. So when you call it in here, x and y, we are not evaluating x to 1 and 2 and passing them into f. We are passing references to x and y. Or it must look like we are passing a reference to x and y. Okay? So here, when you evaluate that, what should you get? You should get a list that has, what, 2 and 1, because f has access to x and y. F has a swap, which is also a macro, so it can swap x and y. So now when you construct this list, these values actually have been renamed in swap to 2 and 1. Okay? So far, so good? Okay. Remember, here is the definition of swap. What it does, this piece of code expands in here, and it just uses set to set x, but this x is actually this one here. Okay? So, okay, if you still remember, what are the 2 pieces of code that we need to find in the program and rewrite to facilitate CBR functions? We may need to rewrite a and b. Okay, but we'll rewrite them differently in 2 different contexts. So what are those contexts?
So you need to worry about accesses and like setback?
We need to, okay, we need to sort of, we need to rewrite reads and writes into those variables. That's for sure. Can we pop up to a higher level of abstraction of what we are rewriting?
We're rewriting the procedure definition and the procedure application.
Exactly. So we do, this is a definition of this procedure. Here we introduce f and give it its body, right? And here is a use, right? Here we call it. There could be multiple calls to f. So you need to set it up in such a way that presumably this defined CBR will be a macro, that this macro, when expanded, will somehow find all calls to f, rewrite them the right way, and also somehow introduce a definition of f. Right? So there are 2 sides, the definition and the use. So all calls to the function, there could be more than one, could be 0, and the definition, the single one, will be rewritten. Okay? So if you still remember, what are the assumptions and restrictions? Warren mentioned that.
They're first order.
They are first order, so we cannot take f and pass it around, and when it is used somewhere, it will still have the CDR semantics. At least not with the simple implementation, but it's still pretty cool. Okay, so here is the result of how we rewrite the calls. So imagine we have this call. Again, there could be many. They could have different actual arguments, not x and y. They could have g and h. Remember, these need to be variables, locations, right? Because we are passing it by reference. So something like plus 1, 2 would not be a legal actual argument. Okay. So we have such a call, and assume that we have already defined function doF. We'll talk about it soon. Assume we have defined it, so we can call it. And so how do we call f? We'll pass it 4 things. Right? What are those 4 things? Getters and setters, and what they refer to, these x and y must be set up in such a way that they bind to whatever x and y binds to, right? So x has some value, right? They will be bound to the same thing, the same memory location, same for this. So at each call site, we generate, through rewriting, through macros, this call with 4 lambdas specially created for this purpose. And this x and y will be taken from here. Right? Macro will match them and then spit them out into these lambdas. Right. Okay, we'll see how to do it, but now we're sort of defining the problem. From such a call, we are going to generate this. So this is our compilation strategy. If x and y had 17 arguments, this will have 34 arguments. We need to generate 34 getters and setters, if I multiply it correctly. Okay, so now to the other side, the definition of f. That's a little bit trickier than the call. So we start with this definition. Imagine it defines f, a, and b with a swap body. The first thing we need to do is define a function doF, right? That will be our function. So this will be our implementation of f, you could say. This is the function that will do the work of f. We define it here, and we give it 4 arguments. Why? Because we decided that when we have a function of 2 arguments, we need 4 getters and setters altogether. So here is 1 getter for A, 1 getter for B, 1 setter for A, 1 setter for B. Okay? And then we need to just plop the body of the function here. Well, but not quite, right? It would be nice if we could just take the body and put it here. It will not quite work, right? Why not? We need to somehow also transform it, massage it so that it does work. So when we call the function, remember the call from the previous slide, we are going to give it these getters and setters, easily constructed. This will be passed over here, and these are our ways of accessing variables A and B. Now swap has some other way of accessing A and B. We have written it assuming that how do we access A and B? With sets and reads, right? So you need to go into swap and replace those sets and reads with references to these guys, okay? So it's just showing what swap is. So this is what you can think of as the inline swap here. How? Because, well, it's already a macro. It uses set of x and y, okay? And now we need to rewrite that into put A. What value are we putting into A? Well, the one that we read using get B. Okay, so we need to do some clever matching here because, you know, swap assumed A, B as the names of the arguments, but when you look inside swap, it uses X and Y as the arguments. But this is what we need to accomplish. Find sets, find reads, right? Here is one read, here is another read, and replace them. Okay. So what we do, the macro for CBR, okay, needs to rewrite this and that. So what will the macro for CBR do? it needs to do two things, right? It's going to introduce two further macros recursively. Okay. So it will introduce one macro for call rewriting and one for definition rewriting of the definition. And those may further introduce other macros, but at the highest level, this is what happens. Okay. So it will be a macro generating macro. You know, nothing much to it. It's sort of a recursive macro expansion. Okay. So here it is. So let's see if you can parse it. I'll let you look at it. Okay, so let's look at it at the top. So this is the simplest form of the three macro definitions, right? Here we are introducing the macro, which will define a function with this name and some argument, 0 or more, and it will have a body, right? So this is the new construct that we are introducing. Here is a begin, which contains two macros. So CBR, as we said, when expanded, will actually define new macros. This one here is for definitions, and this one here is for calls. Okay, and we'll look at this one shortly, but let's look at the one for calls because that's it. This doesn't expand further. So what does it do?
So it basically is going to expand it into a call to do f, which is odd. I mean, it would be nice to have something like do id, but you know, that's besides the point. So it will expand into a call to do f with getters and setters. So the paren with two sets of ellipses in it means take actual and sort of match it recursively, but every single time that you see a new thing, it should be a 2-element list. Why should it be?
Well, so what does it do? So this one matches the actual call, right, with this name. So function f, for example, or g. This is one, actually 0 or more actuals. Why is this 3 double dots? So this is an escape mechanism, right? Because we have a macro here which introduces another macro, right? This is the one that is introduced. And we want these dots to take effect when the inner macro is actually expanded, not when the outer one is. So we do not want the matching mechanism to look at the dots and say, is there a pattern variable in front of them? If instead of this, we just had 3 dots, then these 3 dots would be evaluated by the pattern matcher at the time when this is expanded and these 2 macros are introduced. We want to delay that, and we want these 3 dots to be evaluated when this macro here is expanded at the time of finding a call in the program and expanding the call into the call with the getters and setters. Okay? So this is a way of saying generate a macro that when this macro here is generated, it will have only 3 dots. Sort of like a backslash backslash in string. Once you evaluate it into a string, it is a backslash. And so this macro here, defined syntax, is going to have 3 dots as we want. Okay? Now, what is this call here going to be replaced with? Well, with a call to dof, and the first argument is going to be what? A getter. Okay? What does the getter do? Well, it just reads from the first actual, right? The first actual argument. And the next one right? It will generate a getter for the next argument and the next argument, and they will all be the same. They will be getter lambdas, but they will refer to the next actual. Right? We are doing nothing here. Assume that when this macro is expanded, when it is run, so to speak, we have just 3 dots, which will repeat this for each actual. So we are just wrapping actual in this lambda and inserting them here. So we are creating a call with 1 lambda per actual argument. Okay. And then we do exactly the same, iterating again over actuals, all of them, but now generating the setter function with the formal here that is local to this lambda. And this is the next set of arguments to this call. Okay. So this doF indeed is strange, right? If we define multiple such CBR functions, then they will all use doF because we are not using the ID name in here, right? I actually didn't realize that. So we should construct this symbol using that somehow, right? Or use just ID to create, perhaps. Other functions, I mean, for concatenating
Yes, you can, yeah, but you
from
can,
string, you can construct the symbol.
Yeah, but you can't do the define syntax rule. You have to do the explicit syntax case. You can escape into the macro expansion environment and grab the ID to concatenate it to get a new name.
Right.
Right, so because what you want to do at the point where you're writing doF, what you want to do is actually have an escape there, right? And do a concatenation of the word of the string do with the name of the ID, right?
Yes. Oh, because this is already a template, right?
Yeah.
But in the usual way, right?
Yeah.
Okay.
But this is going to work because of the renaming, right? So even though it looks like doF to us, it's going to be doF, you know, with some rewritten so that all the doFs are going to be unique for each ID.
Oh, I see.
Yeah, because the macros are hygienic.
Even though the expansion for a different function would happen in a totally different sort of parallel rather than nested scope. Oh, okay, great. Thank you. So it looks like we are done with the call. So let's look at what happens inside this macro that takes care of the definitions. So
I mean, how does Packet know that we want it to be a different duet?
I think it will proactively have to do it.
Okay.
I mean, it doesn't care what you want, right? But basically, when you
I mean,
introduce a new name,
when I say plus, when I say plus, how does it know I mean the normal addition procedure plus?
as opposed to, I mean, if you didn't redefine it in a lexical scope to anything else, it has to be that, and if it isn't that, if it isn't defined at all, you're going to get an error.
So I think what it does here is
Okay.
it essentially says these are two uses of the same symbol. They are bound same way in the sort of free variable sense. They are identical, right?
Yeah.
And so we are free to rename them whichever we want, as long as they still refer to the same thing. Excellent.
Why would it say they are bound to the same thing? The define for CBR looks like it's the second argument whenever you call define for CBR. Right? Like the second doF is just the second argument for define for CBR. That's like saying you have X and X that would be bound to the same thing always.
Well, so you're saying this? It does look like a second argument, but what is it? I think that
it's outside that scope, right? Like it's way.
I mean, what is defined for CBR? I'm assuming it's some kind of.
No, this is just a macro that you're expanding here, right?
Yeah.
You can think of it really as if you are just expanding another macro, calling another procedure, passing this as an argument. So you need to make sure that this and that, of course, is the same, because this is going to introduce the definition. So that's a good point, saying that this scope is different than that scope. So you cannot actually find these two guys. Okay, so let's suspend it that at the end we can do an experiment and expand it fully and see whether it renames it or not. Okay, so what are we going to do now? Now we need some way of setting it up such that these sets and reads in any procedure, not just swap, are rewritten. Okay, and now we need a different kinds of rewrite construct. There is called syntax ID rules. Why is it useful? Because it also matches a symbol that is inside, not just in this position. Right? So the matching so far had to be on the left parenthesis. This one can be inside. So it's sort of in the ID position rather than the call position. Okay? And otherwise things look pretty much the same. Essentially we are saying if you find my variable, a specific name, replace it with a call to my get. If you find a set to my variable for some expression, then call my put, give it the same expression. Okay. So far so good, right? Except this is the case that I couldn't quite explain. So now I think I know what is going on. If you use my variable not in the middle. So if you use it here, I don't know, you call something like foo1 with my variable and some expression, then this will be matched by that and replaced with a call to my get. This is fine. But if my get is in this leftmost position, okay, what sort of rewrite do you want? You also want to achieve the same thing. You would like to replace that with a call to, sorry, this should be my var. So you find my variable, you also want to replace it with a call to my get, and the rest should be just copied inside, right? So we want the same effect, except the matching mechanism in Racket is such that if my var is on the left, the matcher will receive the entire expression, including the arguments here. So you do need to have a separate case for my var being inside, here or here, and a separate case when it is on the left. If it is on the left, you will receive this entire form, and you need to copy it over here. So you receive also that, and therefore it is copied over here. So the inside position is handled differently than the left one, in the sense that the match that you get is bigger, you get the entire form, and therefore there needs to be this case, if you care to rewrite such instances. Okay. And in this case you perhaps don't, but in general you may want to rewrite that, right? Because this variable could be pointing to a function, is my get after it is called returns a function, and then it is actually called with the outer parentheses.
Is there a macro which just blindly goes down the tree and replaces wherever it finds a match? So basically no special case for function versus argument?
It seems that it is not, that you do need to distinguish between these two cases.
And that just seems to go against the idea that functions are first class.
Is the order of replacement here defined with the replacement rule providing? It seems like you can come up with cases where the order of replacement would matter.
The first match triggers.
I more mean the order in which the tree is traversed.
It is defined in the sense that the reference manual describes what happens, how you match. If you cannot apply any macro, then you evaluate. Can I reproduce it for you here? No, it's not trivial, I think. especially the business with phases, how things happen in one phase and then another phase is entered. Okay, so it looks like this is fine. Now what we are doing, we take what we have just defined and we make it general, right? Previously we had here my variable, my variable, my variable. We just make it a parameter and we create this macro generating macro which gets these arguments, right, and decides what ID is from here. It gets and put. So this is our define get put ID macro. Nothing more to it, just a wrapper. Okay. Now what do we do with this? Okay. Now remember we have this definition of our CBR function, and now we know what we want to rewrite it into. We want to rewrite it into the definition of this function, okay, with 4 arguments. These will be supplied at the time of the call. A swap here, and here is the macro generating macro, which does what? It goes through whatever code is here in the body, in our case swap, finds A and replaces reads and writes with these 2 functions, and the same for B. Okay.
It seems like this depends on having swap expand before the get put ID. Are we guaranteed that that happens?
I'm not sure we need to expand it before, because it will expand at some point, and then we look at the result of the expansion. We'll find in it sets and reads from those variables, and this is when
I mean, okay,
these
let me
macros
rephrase that. So
okay.
if the define get put ID executed first, we would have code that says swap get one get 2, which would be a problem because swap can only take identifiers.
What would, say it again?
So it would be swap, a call to get 1, well, a call to it, and get 2, a call to get 2.
I see.
And swap can't work with that.
Mm-hmm. So the I see. So the order must be just right. Otherwise, the expansion that we define could happen right there.
So the define ID syntaxes introduces a special thing which is called a make set transformer, and that's handled especially by macro expander, which is why you don't get that problem, right?
Okay, I'll take your word for it.
I mean, they just force the correct ordering, right?
Yeah. So I don't know the answer. So let's see.
So if you go back to the previous slide, Russ,
Mm-hmm.
so that define syntax, the ID and the ID rules, so they create this thing called make set transformer, which is handled specially. Like, I don't actually understand the details, but that's why it works.
So the make set. So I know there is a special handling that I also don't understand for sets. But it looks like we have the problem also for reads. Right? I think the case that is tricky, which is really interesting, is what if we have swap A and B here, right? How do we make sure that this A and B is not rewritten into this and that? Right? Before swap itself is expanded. So so here is what, okay, I think the answer is this. If you look at the order in which things are expanded, they are described in the reference manual as essentially top-down parsing. So the process looks like this, as far as I understand that. The process comes here to swap, right? It looks at swap before it looks at its arguments and say, oh, I have a macro for swap. And it will expand it. And then it will start dealing with its arguments, which you can think of being lower in the tree.
You could define something that doesn't work? Like, what if I wanted swap to the infix? A swap B.
Then yes, you could. So you could, perhaps it handles the common cases in the natural way. But the answer to your question is that this is expanded, I think, before the arguments are. I think that's probably the simplest answer.
Even if it expands A and B to get and get to, why would it create a problem for the swap macro? Would it just take get and get to and put it in place?
So, okay, so the question is, if we expand A and B first, so we obtain this form, and then we expand swap, where is swap? I should have the code for swap somewhere. Okay, so here is our swap, right? Then, after swap expansion, the argument to swap would be the call to get one, and therefore the call to get one would appear here in this position. And so the set would be applied not on a location, but on a call to get one. So that order is crucial, but it is essentially, as far as I can interpret the reference manual, applied on the sort of symbol first and then on the arguments, which is sort of going top down the tree. So this is, yeah, an excellent observation. I'll try to find a better explanation for it. Okay.
The reference just says that using that thing creates this transformer which triggers special cooperation with the parser.
Special, okay.
Cooperation.
I know they handle sets specially, and I don't know how. Yeah, that part was not the best, but well, I'll give you an explanation. I'll dig further into the reference manual. Okay, so what do we need to do to generate this code? So we are pretty close. So now we know what we want to obtain when we see this. So in other words, now we know what this macro should do. Well, this macro expands into these two macros, right? The one for calls and one for definitions. And the one for definitions needs to generate this sort of code. So what tasks remain? So let's look at how we did it here, right? So the define CBR expands into one macro for calls, right? This makes the actual call with getters and setters, and here is the one that will generate for us this stuff, okay? So it receives the name of the function, it receives the list of arguments, okay? Notice that here we are not escaping these dots because we want to call this macro directly with the entire list rather than wait for the expansion when this macro is expanded, okay? Right, so given the name of the function, the list of arguments, we need to do what? We need to generate these unique names, and then for these names we need to generate these calls to further macros. Okay, so again, using this call to the macro with the name of the function and the list of arguments. For each of these arguments, we need to create a unique name and then do this. Okay. So here is how they do it. They do it in two phases. Here is one phase, another phase. Both of them is recursive. Okay. One of them generates the unique names, and the other one, given a list of names, spits out these definitions. Which one's this? Define get put ID, which essentially introduces the rewrites. Okay. Now, one thing that we want to look back at is how are we invoking this macro. It has the usual arguments, name of the function, arguments, but there is also this empty list here. Why do we need it? I can tell you that the first match happens here. Call this macro with a name, okay, and a list of arguments. What does it match to? It matches to this. Sorry, it matches to that, and then it generates this template, right? So on the first call, the first match, this is going to be this empty list, and this is going to be the entire list of arguments. And we'll rewrite it into what? A list that is stripped of the first argument, right? This one is gone, okay? The body is the same, okay? But what we do, we take this empty list and we put in it the argument that we just stripped with get and put. What are these? These will be two freshly generated names. On the next iteration, another ID will be stripped, and that ID will be put at the end of this list. This match here now will contain the previous one. It will be just copied over here, right? These generated names, initially empty, then it has the first triple, will match, and then we append the next one here. So at the end of this phase, when will this one end? Well, when this one is empty, when we emptied all of them, this will no longer match because we require at least one ID here. Right? This is 0 or more, but there is at least one that is required. Right? So at the end of this phase, what do? We'll match this. This list of arguments has been emptied. Here we have a list of generated ID, get, and put names. Right? A lot of them. And the body unchanged. And we match it into what? We'll generate a definition for this name. All these gets are spit out here. These are names of formals for this function. All the puts are here. And now what's in the body of the function? Well, there is the body at the end, but before it, you introduce the macros, right? The define, get, put macros. What do? They do the set and get rewrite. They refer to this ID, this get, this put, and you introduce such a define macro for each triple in this list. So it's amazingly compact. Now let me show you what it does on a run of it. Okay. So we'll call the macro with the name of the function. It has two arguments. This list is initially empty, and here is the body that doesn't change. After the first match, we get rid of one argument, a. Okay. And we put it into this list, a, get, put. See, these are new names, freshly generated. After the second match, B is taken away from the list.
Where did you say generate new names? Like, where did you say in the previous slide that this should be?
So that happens by just the mechanism of making sure that these names are lexically distinct. Because if you look, let me go back. We are referring here to, where are we? To get and put. But we are introducing them again and again as these recursives, and they are just given a fresh name by the lexical conflict avoidance, the hygienic macro mechanism. So we are using that mechanism to create new names. And so when we are done with the first phase, we have emptied A and B. Now the list contains A with the corresponding names for the getters and setters. These are the formals. Now we switch to the second phase. It's actually not recursive. There is just one go. We define the header of the function, get one, get two, put one, put two. These two definitions, right? For A, get and put, B, get and put, and we just dump the body in there. So we use the macro with two phases to generate a macro. Well, it's a definition of a function with macro inside which sets up this rewrite. So everything is very small and concise. Yeah, let's see.
In the previous slide, are you kind of relying on the renaming always being get underscore one and
No.
not? Okay.
The compiler could change the renaming. We are only relying on the fact that the get and put that we get in one invocation of the match, right? This match, this pattern matches, and then we replace it with that. And this happens once for each argument from this list. I'm only relying that each of these invocations will get a fresh name. Now, this could be called foo1, whatever, right? Because we are binding, we are associating the ID with the get and the put name, whatever they are in this triple, and then we are generating the define get put from that triple right here. So the association is preserved through that list. Where is that list? It's here, right? You can think of it as the whole purpose of doing the first recursive phase is to just obtain this list. Okay? And it's sort of a neat way of getting fresh names. Sorry.
Where does the _1 and _2 come from?
So the _1 and _2 is the sort of compilers or the macro expanders mechanism of saying, I'm using get twice. Once when this matches first time, so this is matched, this is replaced, and then this happens again. You can think of it as a recursive call, that on each invocation strips this list of the first element and replaces it with the shorter list. So this get, so this match happens several times, and a fresh name get and put is created. How do they create a fresh name? They give it underscore and some number that makes it guaranteed to be unique.
So it's the feature of the...
Right, right. So this is the feature that is used to make sure that when you use the macro several times, and you have variables with the same names at different levels, they will not clash. And it's used here to get unique names for get and put. Okay? So that's it. Now, let's see if we can actually run it. And I'm curious about this doF, whether we can break it or not. I'm sure you are as curious as I am. Okay. So we went through many slides to understand it, but if you think about it, this is the entire thing that we need to do. Here is the define get put ID. Here is the define CBR, the one that introduces one macro and then for the calls, the one for definitions. Then here is the one for the definitions. That's it. So the entire language of call by reference is on one page. And yes, it takes a while to understand it, but it's a good investment because each time you introduce a language, it's a lot of rewrite. People from the data log team, Peter is here, were really proud of writing rewrite rules for programs and analysis with data log, which of course can be used as a rewriting language. This comes with some extra bells and whistles of mixing rewrites with evaluation. So it should be possible to do things even more concisely. Okay, so so I have here the swap is in here, the actual CBR function that we had and a use of this function. So let's see whether it actually does what it's supposed to. Okay, so it does output the right thing. Now let's see if we can do another one. And we'll do just return the list.
You can't really test call by reference.
What was that?
You can't test call by reference.
The idea is to see
Whether this F and G will clash. I don't know whether
A is not a function.
A is not a function, right? Actually, let's just do this. Should be enough. So G seems to work as required. F seems to work as required. So let's see if we can see the full expansion. So there is this expand step thing, which is a nice debugger. And it should take this definition here and expand it.
Today is the first step.
Yeah.
So this is the first step. I'm not it uses colors to show what the rewrites is does. Okay. So from here it's hard to say whether it did rename it and how, right? Let's see. I would like to see
If you go to
both.
the next step, it will move to G, right? Right now, and as far as G,
You mean I should just replace this with G?
or do both.
Yeah, I think doing both would be nice. Actually, sure. If I hopefully can put them here.
The first argument is a syntax object, the second is
Right, so let's see. What I'll do is make a begin maybe. This should be okay. Okay, so here is F, here is G. Let's see, now we should see something. Let's look at the final form. So they do have different colors, right? And highlighting one doesn't highlight the other, so they are in different scopes. So let's see where that happened. Okay. So here we start working on G, and we already have a different doF. So I think the hypothesis that when first time we see first time this symbol is introduced, it is going to get a different renaming, but it must be in the same scope as this. And I think it does make sense because it looks like this one is nested, but really we are defining this construct at this level.
It's not nested. So basically what happens
Mm-hmm.
when that doF in the nested part doesn't get triggered until the expansion at the call site.
We
And
should
at the time that's expanded, you have defined for CBR doF already in scope.
Okay, so we come here. Now, actually, the names must be bound together. So they must be in the same scope.
They are in the same scope. I mean, that defined syntax, the syntax ID thing, all it does is introduces a binding from that name into the transformer environment.
Uh-huh.
And that does the renaming. So they're in the same scope. It just looks like they're different because of the way it's parenthesized, right?
Right. So I think that's our explanation. That this must be introducing symbols that remain at the level of the same lexical scope, and this is why the renaming works. Right. Okay. Good. So we learned again a lot more, and I think that's it for macros. From now on, we'll just look at application of them. But this should be, I think, deep enough exposure that the remaining gotchas you should be able to find through the manual and so on. I want to show you one other thing. Actually, there is one more slide. So perhaps you didn't like this trick, relying on the internal renaming, which avoids conflicts to generate temporaries. Well, it could be done more directly, and here it is. Here it's how. So let's walk from the top. We again define syntax which defines this helper macro for us, define for CBR, which introduces these new names. And now the syntax case does what? When we find this doF with, right, so we find this definition of doF with its arguments, we generate temporaries. There is a helper function. You see, this is at the racket level. So you just call a library with a piece of syntax which contains a list of these identifiers, and we generate a list of fresh temporaries for us. And what do? We assign it to a correspondingly large new set of symbols, and the same for put. So you can think of it as we introduce a bunch of variables into which we bind one by one these temporaries, and these variables here. Okay. The one special thing is that what are these variables? These are not racket variables, but because of this construct, these are those pattern variables that are available at tree matching time, at macro expansion time. So using let, you can introduce variables in sort of racket evaluation time, and using with syntax, you can introduce variables that you know are available to macro expansion. And this is sort of plain, boring stuff. Call the library, give it a list of symbols, and it will give you back fresh temporaries. And now you do the rest the same way. Define, introduce this macro for each ID get put, repeat it. And so the interesting thing is here that you can actually create your own macro level template variables. You don't need to rely on the matching mechanism to introduce them, right? This ID is a template variable introduced as a result of this matching, but you can introduce it yourself. So that's it. That might be useful to compact everything and make it much more readable. Okay, so it's a powerful tool. Now we just need to start using it. Okay, that's it for today. Thank you.